In section 10.6, we're going to continue on with solving trig functions. In this section, the focus is going to be on listing all the solutions and also solving trig equations where the argument is not just an x. So it could be an x over 2, or it could be 2 times x. So let's just jump in. In example 1, we want to solve. We're going to first, in part A, list all the solutions. Our equation is sine of x times cosine of x is equal to 1/4. Now, again, the goal is to try to get just one trig function in your equation. In this case, it would be really hard to replace the sine with something that's only cosine, or the cosine with something that's just sine, because you're going to end up with a plus minus square root with a bunch of stuff underneath it. So it's actually going to make it more complicated. So in this case, what I do notice is that sine of x times cosine of x, that's almost one of our identities. If this were 2 sine x cosine x, then that would be equal to sine of 2x. So this is an equation. I'm just going to multiply both sides of the equation by 2. And then on the left-hand side, this becomes sine of 2x. It's going to be equal to 2 over 4, or 1/2. So now, ignoring the 2x, sine is 1/2, positive 1/2 in quadrant 1 and in quadrant 2. So if 2x is in quadrant 1, it would be pi over 6. If 2x is pi over 6, then I have sine of pi over 6 is equal to 1/2. So one solution would be that 2x is equal to pi over 6. But remember, we're supposed to be listing all of the solutions. And the period for sine is 2 pi, meaning if I add 2 pi to pi over 6, or I subtract 2 pi from pi over 6, I will get back to the same place where it's going to be equal to 1/2. And it could be multiples of 2 pi. It could be 4 pi, or 6 pi, or negative 4 pi. So the way we would write that is we would add 2 n pi, and here n is just any integer. So let's write that down here. N is an integer. And then when we say integer, we're talking about -3, -2, -1, 0, 1, 2, 3, and so on. But remember, there's also another positive solution for sine, and that would be in quadrant 2. In quadrant 2, that would be at 5 pi over 6. So the other solution would be when 2x is equal to 5 pi over 6 plus multiples of 2 pi, so 2n pi. But we're supposed to be solving for x, not 2x. When we look at the interval, the 0 to 2 pi, these are x values, not 2x values. So at this point, what I would do is I would just divide everything by 2 in both of these equations. So divide by 2 to get the x by itself. Once we do that, we're going to have x equal to pi over 12 plus n pi. That's one solution. The other solution would be x equal to 5 pi over 12 plus n pi. And this would be our part A. We found all possible solutions. In part B, it says list all solutions just in the interval from 0 to 2 pi. So notice that in my solutions from part A, the denominator is 12. I have pi over 12 and 5 pi over 12. So you may, and this is not necessary, You may want to write 2 pi as denominator of 12 would give me 24 pi over 12. And you'll see why in just a little bit. It's easier for me to determine if my solutions are in the interval or not when the denominators are consistent. So when we're looking at part B, write this down. We're going to list all the solutions for x values from 0 to 24 pi over 12. So if you look at the first equation, x equal to pi over 12 plus n pi, if n is equal to 0, we have pi over 12 as one of our solution, and that is in the interval from 0 to 24 pi over 12. If n is equal to 1, I'm adding pi to pi over 12, so that gives me 13 pi over 12. And that's still within the interval. If n is equal to 2, it's pi over 12 plus 2 pi. That will give me something that's too big. That will give me 25 pi over 12, which is outside of my interval. Anything that has a numerator smaller than 24 pi will work, but if the numerator is larger than 24 pi or 24 pi, then it's not going to work. So now I'm going to go to the next equation, x equal to 5 pi over 12 plus n pi. And if n is equal to 0, I get 5 pi over 12. So that is in my interval. If n is equal to 1, it's 5 pi over 12 plus pi, which would be 17 pi over 12, still in the interval. If n is equal to 2, it's going to be 5 pi over 12 plus 2 pi, and then I'm outside of my interval. So these are just the solutions for x within that interval from 0 to 2 pi. And you can always check these solutions by putting them back into the original equation, or even the sign of 2x equal to 1/2. You can either check them by plugging them back into sign of 2x equal to 1/2 and seeing if they make them true or not. And they do. If you put in pi over 12, times it by 2, you get pi over 6. Sign of pi over 6 is 1/2. So you could check all of them and they'll work. Let's do another one. In example 2, again, we're not using a calculator. We're going to first list all the solutions, and then we're just going to list the solutions in the interval from 0 to 2 pi. So same thing we did last time. We have sign of x over 2 is equal to 1. So when I look at sign of x over 2 equal to 1, I've already got the sign by itself on one side of the equal sign equal to some number. So I'm pretty much done. Now, if I just look at sign, oh, I don't want that. If I just look at sign and kind of ignore the x over 2, sign is equal to a positive 1 at pi over 2, right? So that would be pi over 2. And that's the only value where sign is equal to a positive 1. So my solution, but it's an x over 2, is if x over 2 is equal to pi over 2, then that's going to be a solution. However, remember, we're looking at all the solutions, so we're going to be adding multiples of 2n pi. Again, similar to what we did last time, we don't want x over 2, we just want x. In this case, what I'm going to do is I'm going to multiply both sides of the equation by 2 to get the x by itself on the left-hand side. Multiplying by 2, I get x equal to, so don't forget you're distributing that 2 to the pi over 2 and also to the 2n pi. That would give me pi plus 4n pi. And that would be my part A, all solutions. B, let's list the solutions for x values from 0 to 2 pi. So again, that's the interval that we were given. If n is 0, pi is a solution. And again, you could put pi back in for x in the original equation, right? You can always check it. If you put pi in for x, you have sine of pi over 2, which is equal to 1. It works. If n is equal to 1, then I have pi plus 4 pi. That's 5 pi. I'm already outside of my interval, so I need to stop there. And actually, the only solution in that interval for x is pi. And let's do some more solving. Example 3, we have cosine squared of x over 2 minus 1 is equal to 0. My first thought is to get the cosine squared of x minus 2 by itself by adding 1 to both sides and then kind of seeing what's going to happen after that. So we have cosine squared of x over 2 is equal to a positive 1. Now I'm going to square both sides to get the cosine of x over 2 by itself. But don't forget, if you're squaring both sides, you have to add the plus or minus, and this becomes the square root of 1. But the square root of 1 is just 1, so we have cosine of x over 2 equal to plus or minus 1. So we have two things we have to consider. We have to look at the cosine when it's equal to 1 and cosine when it's equal to negative 1. So if you think about that, cosine is equal to 1 at 0, and then at 2 pi, but 2 pi is already too big because we're only looking at the interval from 0 to 2 pi, but not including 2 pi. And then negative 1 would be at pi. Our two solutions then would be x over 2 equal to 0 plus the period of cosine is 2 pi, so 2n pi. And the other solution would be x over 2 equal to pi plus 2n pi. Again, we don't want x over 2, we want x, so we would simply multiply everything by 2 in both of these equations to get x equal to, and I'm going to ignore this 0 here. Adding 0 to anything is not going to change it. So 2 times the 2n pi would be 4n pi. And then this becomes x equal to, don't forget you're distributing the 2, so it's going to be 2 pi plus 4n pi. And that would be our part A. Part B, we're supposed to list all the solutions in the interval from 0 to 2 pi. The first equation, x equal to 4n pi, if n is 0, then the solution 0 works, it's in the interval. And I could plug that back into the cosine squared x over 2 minus 1 equal to 0 equation and see if it makes that equation true, and it does. If you put in 0 for x, it's cosine squared 0, which is 1. 1 minus 1 is equal to 0. So yes, it's a solution. Now, if n were equal to 1, that means x is equal to 4 pi, and I'm already out of my interval because my interval only goes to 2 pi. If we look at the second equation, which is 2 pi plus 4n pi, if n is 0, we're at 2 pi, which is too big. So I can stop. 0 is my only solution for x in the interval from 0 to 2 pi. And one more time. So in example 4, we have 2 times cosine of 2x equal to the square root of 3. First thought is to get the cosine of 2x by itself by dividing everything by 2. And I'll have cosine of 2x is equal to the square root of 3 over 2. Okay, so cosine, again, I'm ignoring the 2x. I'm just thinking, when is cosine equal to square root 3 over 2? So that would be positive. So it's quadrant 1 and quadrant 4. In quadrant 1, square root 3 over 2, that corresponds to pi over 6. And in quadrant 4, that corresponds to 11 pi over 6. But remember, the argument is 2x. So that's going to be equal to pi over 6 plus 2n pi. And 2x is equal to 11 pi over 6 plus 2n pi. Dividing both sides by 2 to get the x by itself, I'll get x equal to pi over 12 plus n pi. And this is my part A. And then x is equal to 11 pi over 12 plus n pi. So I have all solutions. We'll go to part B. In the first equation, pi over 12 plus n pi, if n is 0, I have pi over 12, which is in my interval from 0 to 2 pi. So remember, that's the same as 0 to 24 pi over 12. So once my numerator is 24 pi or larger, then I'm outside of the interval and it won't work. If n is equal to 1, I have pi over 12 plus pi, which is 13 pi over 12, still in my interval. If n is equal to 2, it's pi over 12 plus 2 pi, and that's too big. Let's go to the second equation, x equal to 11 pi over 12 plus n pi. If n is equal to 0, 11 pi over 12, we're in our interval. If n is equal to 1, it's 11 pi over 12 plus pi, which would be 23 pi over 12. Still okay. And then if n is equal to 2, it's too big. So those would be our solutions. Again, you can always plug those x values back into the original equation and see if it makes the original equation true. And all of these will. Example 5 says that we want to solve 1 minus sine of x equal to cosine of 2x. In this particular example, I think what I would like to do is maybe replace the cosine of 2x. Because remember, we have those 3 different identities with the one that only has sine in it. So at least I can write this equation so that there's only a sine as my function. You don't have to do it this way. So I'm going to replace cosine of 2x with 1 minus 2 sine squared x. And now I see a sine squared and a sine. That tells me maybe it's going to factor. It looks quadratic. So what I'm going to do is I'm going to bring everything over to the left-hand side. But first of all, look, as if you minus 1 from both sides, that's gone. So if I add the 2 sine squared to both sides, I get 2 sine squared x minus sine of x equal to 0. So I've moved everything over to the left-hand side, set it equal to 0, and now I can factor out the common sign. What's left would be 2 sine x minus 1 equal to 0. And now, since it's factored equal to 0, I can set sine of x equal to 0 and 2 sine of x minus 1 equal to 0. Sine of x equal to 0. Oh, and I don't have to worry about the argument. It's just x because I replaced that cosine of 2x in the beginning with something that just had the argument of x. So I don't have to adjust it. I don't have an x over 2 or a 2x that I have to worry about. Sine is equal to 0 at pi. So I'm going to have x is equal to pi, but I have to add in the 2 and pi to get all the solutions. Oh wait, I forgot that it's also equal to 0 at 0 plus 2n pi. So I actually have two sets of solutions when sine of x is equal to 0. And then if we look at the 2 sine x minus 1 and we get the sine x by itself, by adding 1 and dividing by 2, I get sine of x is equal to 1/2. That happens when x is equal to pi over 6 plus 2n pi, and when x is equal to, that would be quadrant 2, so it would be 5 pi over 6 plus 2n pi. So these would be all the solutions, and you don't really need to write that 0 in there, but I'll leave it in there because it's fine. Let's see, we're supposed to find our specific solutions in the interval from 0 to 2 pi. So I've got 4 equations to worry about. Let's see, that would be our part B. I'm going to look at this equation here, x equal to 0, which I don't really need the 0 there. X equal to 2n pi. If n is equal to 0, 0 is the solution. Again, you could put that back into the original equation. That would be 1 minus 0 equal to 1. Yeah, that's true. If I put in 1 for n, I have 2 pi, which is too big. So I am going to look at this equation pi plus 2n pi. If n is equal to 0, I get pi, which is in the interval. If n is equal to 1, I get pi plus 2 pi would be 3 pi. It's too big. Now, I'll look at the pi over 6. If n is 0, we're at pi over 6. That works. If n is 1, pi over 6 plus 2 pi, too big. And then looking at that last solution, 5 pi over 6, when n is 0, that works. Let's see, if n is 1, it's too big. So I get those 4 solutions. Okay, our final problem in this section is square root of 2 cosine of 3x minus 1. So the argument here is 3 times x. I'm going to add 1 to both sides and then divide by the square root of 2 to get that cosine of 3x by itself. That'll give me cosine of 3x equal to 1 over the square root of 2. And I could see that I need to rationalize this denominator to get cosine of 3x equal to the square root of 2 over 2. So cosine is positive in quadrant 1, quadrant 4. This gives me 2 solutions. The solution in quadrant 1, now remember this is a 3x, is going to be pi over 4, and then plus 2n pi. So that would be one solution. The other would be the 3x equal to, in quadrant 4, that would be 7 pi over 4. So that's 7 pi over 4 plus 2n pi. And now I'm going to divide everything by 3 to get the x by itself. And I'll do this in both equations. That gives me x equal to pi over 12. So often we have 12 in the denominators, and this becomes 2n pi over 3. x equal to 7 pi over 12 plus 2n pi over 3. So I'm looking at the pi over 12 and the 7 pi over 12. That tells me that the interval I'm looking at is 0 to the 2 pi becomes 24 pi over 12. All right. So here is our part A. Those are all of our solutions. And now we'll be working on part B. Typically, the larger the number is in your argument that you're multiplying your variable x by, the more solutions you have. So notice that the argument for cosine was 3 times x. So that means that when I'm finding my solutions, I'm actually dividing by 3 to get the x by itself. And whenever you're dividing by a number, you're actually making things smaller, so it actually gives you more solutions. But if you get that 2n pi and you make it bigger by multiplying, then you have less solutions. Because things are already large and a lot of them are already outside that interval. Anyway, let's go ahead and I think I'm going to have a lot of solutions here. Let's go ahead and look at our first equation. If n is equal to 0, I say I have pi over 12. Not a problem. But that 2 in the numerator and that 3 in the denominator for the 2n pi over 3 is kind of throwing me off. So let me look at what happens when n is equal to 1. So if n is equal to 1, this is pi over 12 plus 2 pi over 3, and then I would have to multiply by 4 top and bottom to get the common denominator. This is 8 pi over 12. So pi over 12 plus 8 pi over 12, that would be 9 pi over 12. And that's within that interval from 0 to 24 pi over 12. But 9 pi over 12 can reduce by 3. That would give me 3 pi over 4. So you should simplify fractions whenever possible. Let's look at what happens when n is equal to 2. So if n is equal to 2, this is going to be pi over 12 plus 2 times 2, that's 4 pi over 3, multiply by 4 to get the common denominator, that's 16 pi over 12. So pi over 12 plus 16 pi over 12 is going to be 17 pi over 12. That's still within that interval. Okay, so when n is equal to 3, if I look at the 2n pi over 3, if n is equal to 3, that's 6 pi over 3, which is 2 pi. So 2 pi plus pi over 12, that's going to be too big. I'm going to be outside of my interval. Let's go on to the second equation. And I'm going to kind of keep those original values in red, the n is equal to 1 and n is equal to 2, because I'm going to refer back to those. So if n is equal to 0 in that second equation, we just have 7 pi over 12, which works. If n is equal to 1, this is going to be 7 pi over 12 plus, when n is equal to 1, it became 8 pi over 12. So I'm referring back to what I did prior. And that would give me a 15 pi over 12, which I can reduce by 3 to be 5 pi over 4. And then when n is equal to 2, this becomes 7 pi over 12 plus 16 pi over 12. And then that would give me 23 pi over 12. That's still within my interval. If n is equal to 3, too big. And I have 1, 2, 3, 4, 5, 6 solutions. Okay, so that is it for this section.